So guys, welcome you all to this video. Here we will start a very important topic, namely infinite series. Infinite series of real numbers. Fine. Of real numbers. Questions are frequently asked from this area in any competitive exam or any PhD entrance exam. So it is a very important topic, and you should have proper understanding of this topic from the very beginning. That's why I will start this topic more explicit way so that you can grab the concepts. Fine. So let's get started with it. First of all, you should be familiar with this symbol summation an. Summation an, it is from n equals to 1 to infinity, and here an is the nth term of our series. Okay, so if you write it in explicit form, it will be like this way: an plus so on up to infinity. Okay, now this is your series, and here all of these ai's, that is a1, a2, a3, an, these are all real numbers. That's why this is series of real numbers. If suppose a1, a2, a3, these are complex numbers, then you will have series of complex numbers. But in our videos we will only focus on series of real numbers. Correct? All right. Now here one very important term, it is called nth order partial sum sequence. Nth order partial sum sequence. What do you mean by nth order partial sum sequence or nth partial sum sequence of an infinite series? It means that take the first n term of our series and just do the summation like this way and denote it by Sn. So your Sn equals to a1 plus a2 plus a3 up to this nth term, and this sequence we denote it by Sn, and this Sn is nothing but our nth order partial sum sequence. So what is the importance of this nth order partial sum sequence? It is very important. Suppose you are asked to find what is the sum of an infinite series. Say our series is convergent. Okay, then what will be sum of our infinite series? Then this, particularly this Sn, comes into picture. So basically limit of this Sn will give us sum of our infinite series. Alright, indirectly we have suppose limit of this Sn as a finite quantity, then we can claim that our series is convergent series. Fine. So basically with the help of this Sn we can easily find a sum of an infinite series, of an convergent infinite series. Correct? So with this basic understanding we have some properties of our S and some examples we will also cover up here. Let's take one very simple and straightforward example. So the first example number 1, find sum of this series 1 by r into r plus 1. R runs from 1 to infinity. Alright, so what will be sum of this series? In fact, this is a convergent series. So how to test the convergency? We will tackle it in our subsequent videos. For that we have certain tests in our hand, but here our only duty is that to find the sum of this series. assuming that this series is convergent. Obviously it is convergent, and we will also cover up that part, but here our job is to find simply the sum. So in this case Sn will come into play, because here this is our AR. Alright, so AR means 1 by R into R plus 1. This is our AR. So in this particular example, what will be Sn? Can you give me the answer? So Sn equals to A1, A2 up to An. This will be An. So your duty is to calculate this expression. So let's calculate it. It will be 1 by 1 into 2. 1 by, do it yourself and check whether you are getting the same thing or not. Up to 1 by n into n plus 1. Fine. So now what we can do after this step, we can easily do it like this way: 1 by 1 into 2, 1 by 2 into 3 plus 1 by 3 into 4 plus, it is going on like this way, n into n plus 1, and this term, this is our Sn. So this one we can easily write it 1 minus half, plus here we have by 3, plus here we have by 3 minus 1 by 4, and it is going on like this way. So ultimately, just observe it carefully, and ultimately what we have 1 minus n plus 1. So this is nothing but our Sn in a partial sum sequence. In fact, if you take the limit both sides, you will find that you are getting 1. So this is sum of given series. This is the technique by which we can find sum of any convergent series, obviously with the help of our Sn. Okay, this was one very straightforward and simple example. Fine. Similar kind of examples are there in your textbook, so I will recommend you that you go to any mentioned textbook and study few examples regarding this concept. Okay, fine. With this understanding in our hand, we are moving on to some key points regarding this Sn. So it is this point that if limit of this Sn as n tends to infinity, if this one is plus infinity, suppose limit of this nth partial sum sequence is plus infinity, that immediately implies given series diverges to plus infinity. So it is divergent and diverges to plus infinity. If it is minus infinity, that implies given series diverges to minus infinity. If this Sn is oscillatory, that implies the given series is oscillatory. Two possible cases are there: oscillatory finitely or oscillatory infinitely. Both of them will hold. So let's study few examples regarding these three results. Okay, so our first example, it will be, just consider example number 2 of this video. Just consider summation r, where r runs from 1 to infinity, this one. So in this case we have AR as equals to R, and obviously Sn will be A1 plus A2 plus A3 plus up to An. So it is 1 plus 2 plus 3 plus up to n. It is n into n plus 1 by 2. Alright. So this is your Sn. Sn equals to n into n plus 1 by 2. It tends to infinity as n tends to infinity. Alright. Thus, what you can conclude? You can conclude that your given series, this is the given series and it is divergent and diverges to plus infinity. Fine. This is another very straightforward and simple example to understand the concept. Fine. Okay. Now there are plenty of examples are there. Obviously you should study. Another very important and a trivial example is example number 3. So it is summation minus 1 to the power, say r plus 1, r equals to 1 to infinity. So what you will have, look at 1 minus 1 plus 1 minus 1 plus 1 minus 1 and so on. It is going on like this way. Fine. So what will be your Sn? Look at, in this case our Sn will be 1 if n is odd. Sn will be 0 if n is even. So in the case of limit of Sn will be 1 when n is odd and it will be 0 when n is even. So by our discussion that if limit of this Sn, in fact this Sn is oscillatory, then immediately what we can conclude that our given series, this series, it is also oscillatory. In fact it is oscillating finitely. Okay. Now here is another example, that is example number 4 for oscillating infinitely. Oscillatory series, oscillatory infinitely. Can you give me one example? Think about it and let me know in the comment section. I will give you one hint here that with the help of this series, that is example number 3, you can easily construct an oscillatory series which is infinitely oscillatory. Okay, so you just need to think a little bit. With the help of this third example you can easily construct it, and also don't forget to mention it in the comment section. Okay, fine. So up to this is for today's video, and in the next video we will deal with another very interesting topic regarding this chapter, to very important series and very famous series as well. So the first series, it will be geometric series. We will study geometric series and you are all familiar with this geometric series, and the second one is P series. So these two topics are going to be very interesting because we will discuss these two topics from the very beginning so that you can easily grab the concepts, and these two part will come again and again in this chapter and as well as in the later section as well. So in our next video we will focus on this